Sir, screen is visible.
Yes.
Hello, hello everyone. My name is Sachin G. Kumar. I have completed MA English and currently I am pursuing Master Certificate Program in Artificial Intelligence at Sri Shankaracharya Computer Center and Vidyan AI and DSS School. Today I am going to discuss about machine learning and its regression model case study and other basic things. This is my case study topic: agriculture crop yield prediction using machine learning and regression model. This introduction. The crop yield prediction is a crucial aspect of modern agriculture, helping farmers, policymakers, and researchers make informed decisions about food production and resource allocation. With the growing demand for food and the increasing impact of climate change on agriculture, predicting crop yield accurately can improve efficiency, reduce food waste, and enhance food security. Yeah. Traditionally, yield estimation methods rely on historical trends, weather conditions, and manual surveys, which can be time-consuming and often lack precision. However, machine learning offers a data-driven approach, leveraging large data sets and advanced algorithms to generate more accurate and reliable predictions. In this project, we utilize machine learning and techniques to predict crop yield based on historical agriculture data, including factors such as area, crop type, and year. This study demonstrates the power of machine learning in transforming agriculture, making it more efficient, sustainable, and resilient to environmental challenges. These are the advantages of crop yield prediction. First one, the improved agricultural planning. Second one, mitigation. Third one, data-driven decision making. Fourth one, cost efficiency. Fifth one, climate resilience. And the disadvantages are: first one, data quality issues. Second one, lack of real-time data. Third one, complexity in feature selection. Fourth one, computational costs. These are the models we used in this project. First one, random forest regressor, is a powerful ensemble learning method that reduces overfitting and provides high accuracy. Second one, gradient boosting regressor, is an advanced boosting technique that improves prediction accuracy by sequentially correcting errors. Third one, decision tree regression. It is a simple and interpretable model that captures nonlinear relationships but is prone to overfit. These are the key observations from data analysis. First one, correlation analysis. Second, after removal. Third one, future engineering. Fourth one, data standardization. And the fifth one, performance evaluations. Conclusion: the crop yield prediction project successfully demonstrates the effectiveness of machine learning in forecasting agricultural yield. By analyzing historical agriculture data, we identified key factors influencing crop yield, such as area, crop type, and year, enabling better decision making for farmers, policymakers, and researchers. The study highlights the importance of data pre-processing, including handling missing values, removing outliers, and feature selection to improve prediction accuracy. Expert data analysis provides valuable insights into yield distribution and the relationship between different agricultural factors. Yeah. The accurate crop yield predictions can help optimize resource allocation, minimize food waste, and support sustainable farming practices. This project reinforces the value of data-driven agriculture in enhancing productivity, food security, and climate resilience. Next, we discuss about the case study. This is a case study. I think ML crop yield prediction using regression model. This is the data set we used. Here we discuss about the data set. Here the data set used for the crop yield prediction project contains essential agriculture factors influencing crop productivity. It includes variables such as temperature, rainfall, pesticide usage, soil quality, and fertilizer application. Along with the crop yield measured in hectograms per hectare, these features help in understanding the relationship between environmental and agricultural conditions affecting crop production. The dataset serves as a valuable resource for predictive modeling, enabling farmers and policymakers to make data-driven decisions to optimize yield, reduce resource wastage, and improve sustainability in farming practices. By analyzing these datasets using machine learning and deep learning techniques, we can uncover patterns and trends that help forecast future crop yield under varying conditions. This is a step-by-step machine learning case study for predicting crop yield using the pre-merged dataset that is ULTF.CSV. Here this is one. Firstly, we import the libraries using pandas, numbing, seaboard, matplotlib, trying to split library and code standard scale edits, regression models, and evaluation matrices. Here, its purposes are firstly we import the pandas. While its purposes is to use it for data manipulation and analysis. Second, using NumPy. Its purposes is to provide support for large multi-dimensional arrays and numerical computations. Third one, Seaborn's purpose used for creating static, animated, and interactive plots. When we go to the Matplotlib, its purpose is to creating plots, and Seaborn's purpose building on top of Matplotlib, it provides statistical data visualizations. Examples are heatmap, correlation matrices, and boxplot. And the trained test splits. Its purpose is to split the dataset into training and testing sets. And next we import the label encoder and standard scaler. The label encoder, its purposes is to encode categorical labels as integers, and the standard scaler, it standardizes features by remaining the mean and scaling to unit variances. And others is a regression models. This is evaluation matrices. Firstly, we load the dataset using this function. This is a dataset URL, and we print the first 5 rows of the dataset using this header function. And we check the shape also. It's the shape of this dataset, and we drop the unnecessary columns using this dropper function. This is the unnecessary column, unlabeled 0. And we find the information of this dataset using this .info function. And we finding the missing values. After finding the missing values, if there is no missing values exist. And next, we using this describer function. This code provides summary statistics. This count the mean, standard deviation, minimum, 25%, 30, 50%, 25% for numerical columns in a data frame. Next, using this function, this code uses label encoder to convert categorical variables, that is area and item, into numerical values. It assigns a unique integers to each category, enabling ML models to process categorical data in numerical form. This transformation allows the dataset to be used effectively in various ML algorithms that require numerical inputs. Next, the remove outliers. Remove outliers function effectively applies the IQR method to detect and remove outliers from specified numerical columns. It calculates the first Q1, the third quarter, that is Q3, computes the IQR and filters out values lying beyond 1.5 times the IQR range. The use of a Boolean mask ensures efficient filtering without modifying the original data frame. However, a few enhancements can improve its flexibility and robustness. Adding a parameterized multiplier allows users to adjust the strictness of outlier detection, and returning a copy of ensures that the original dataset remains unaffected Additionally, incorporating handling for columns with low variance or constant values can prevent unnecessary removals. These refinements make the function more adaptable for different datasets while maintaining accuracy and efficiency. Can we create a box plot for before and after outlier removals? In this plot shows that this code creates a side-by-side comparison of box plots to visualize the distribution of crop yield, that is HG and HA yield, before and after outlier removals. Using Matplotlib and Seaboard, it first creates a figure with the two subplots arranged in a single row. The first subplot displays a box plot of the original dataset, is cropped, highlighting the presence of outliers with a wider spread, while the second subplot shows a box plot of the cleaned dataset, cropped underscore cleaned, where extreme values have been removed, resulting in a more compact distribution. The plot.title underscore layout of function is ensures proper spacing between the plots and displays and visualizations. And next, we create a heat map. Say heat map. This given code generates a correlation heat map to visualize the relationship between different numerical features in the crop dataset. The dataset. It first creates a figure with a specified size of 10^6 inches using matplotlib. Thus, SNS.heatmap of function from Seaborn is then used to plot the correlation matrices of the dataset, which quantifies the strength and directions of linear relationship between variables. The N not equal to true parameter ensures that correlation values are displayed within the heat map cells, while CMAP equal to pool 1 applies a color gradient ranging from pool, that is negative correlation, to warm, that is a positive correlation. Negative to positive correlations. The FMT equal to 2F argument formates correlation values to two decimal places for better readability. This heat map helps identify strong correlations, potential multi-correlative, and insights for future selection in predictive modeling. Next, we create a histoplot. This code effectively visualizes the distribution of probability, that is HG/HA underscore yield. This means hectogram per hectare yield using a histogram with a KDE, that is current density estimate overlay. The SNS.histoplot function creates the histogram where KD equal to true, ensures a smooth density curve is added to show the underlying distribution. The color of the bars is set to blue for better visibility. The fixed size equal to 8.5 adjusts the figure size for better readability, and the plot is labeled with an appropriate title and axis labels to enhance interpretability. This visualization helps in understanding the spread and tendency and potential skewness of the crop data. Here, the x value is crop yield, y value is frequency. And next, we create a box plot. Here, this code create a box plot to visualize the distribution of crop yield, that is HG/HI yield, for different crop types, these items. The box plot displays the center tendency, spread, and potential outliers of crop yield for each crop type. The x-axis represents the crop types, while the y-axis shows the crop yield in hectogram per hectare. By rotating the x-axis, labels this yield.x of rotation equal to 45. The plot ensures that crop names are readable even if they are long. The plot is well labeled with the title and access labels to clearly communicate the data being utilized. This allows you to compare the distribution of yield across different crop types and identify any variations or outliers. Next, that is we discuss about future and target. Here we split future and targets. Also, we discuss about this. The crop dot columns equal to crop dot columns dot string of function. Here the line the crop dot column is removes any leading or trailing spaces from the column names in the crop data frame. This is useful for cleaning the dataset, as column names can cause issues when performing data operations by stripping those spaces. It separates feature of X and target to Y, with X contains all columns except HG/HA underscore yield, and Y contains the HG/HA underscore yield of values. And next, we speak to the train test using this course. 80% train and 20% test. And next, the standardize. This course analyzes the features by scaling both the training and test data, ensuring they have a mean of 0 and a standard deviation of 1. Next, we discuss about the regression models. We will be using a forest regressor, random Gaussian regressor, and decision tree regressors. First, we initialize the random forest regressor using this. This is a random forest model, and we train the model using this external battery. And we predict on the test set, its test, and we evaluate the model using MSC score and auto scores. And we print the random forest matrices, evaluation matrices, MSC and auto scores. We are using the same steps we discuss. And this is also the same step we discuss. And we compare the model performance in one place. Some models we use random forest, Gradient Gaussian, and decision tree. This is a evaluation matrices we use MSC and auto score. And when we display the results, this is a visualization of the performance based on the MSC and auto score. And then we sort the scores in descending order and ascending wise. Here, the lowest MAE and MSC is a better model, it is indicating lower errors, and the highest R2 score is a better model. Based on these scores, best model, and the forest regress is the best model for probability prediction. In this case, it has the highest R2 score, that is, this is high R2 score, 98,570H, meaning it explains a large proportion of the variance in the data. And it also has the lowest MSC, that is 1.03668, indicating the smallest prediction errors. Last, the conclusion. The crop yield prediction project successfully demonstrates the use of machine learning techniques to predict crop yield based on historical agriculture data through comprehensive data cleaning and pre-processing outliers numerical features such as HG/HA underscore yield and year were identified and removed using the IGR method, ensuring a more reliable data set. The categorical variables including area and item were labeled and coded for model compatibility. While numerical features were standardized to enhance model performance, the EDA provides valuable insights into the distribution of crop yield across different crop types and regions, revealing important patterns and relationship between features. Three machine learning models, random forest regressor, gradient Gaussian, and decision tree regressor, were trained and evaluated to determine the most effective approach for yield prediction. Among these, random forest regressor exhibited the best performance, achieving the highest R2 score and lowest CMS score, making it the most reliable model for accurate yield forecasting. The results indicates that machine learning can significantly enhance crop prediction, providing valuable insights for farmers, policymakers, and agriculture researchers to improve decision making and optimize crop productions. The other future improvements, such as incorporating additional variables like soil quality, weather conditions, and irrigation data, along with fine tuning model hyperparameters could further enhance prediction accuracy. This study highlights the potential of data-driven decision agriculture in ensuring food security and sustainable farming practices through advanced predictive analysis. And then last, if you want to know more about this, this is my GitHub link. It also has other similar model case studies and YouTube explanation videos. Thank you.